Okay, thank you. Hi everyone. Today we're going to present our work for like the last weeks that we've been working on. So this is the things we're going to talk about today. This is the paper that we picked, which is a deep convolutional neural network for the early detection of heart disease by these authors. This paper came out around like 3 years ago, something like that. So just a very quick introduction, maybe we are all familiar with that. Tumors, cancer, and heart disease is one of the most things that cause death, at least nowadays. The diagnoses come usually from taking images, right, and then diagnosing the situation. We can use machine learnings, as it has probably been used in the past, by training these images on the machine learning algorithms, and the machine learning predicts the outcome. So in here they use the deep convolutional neural network, or DCNN, which is, it's basically multiple layers, and each layer has like more classification, more complex, in a more complex way. It basically uses like filters, and the output of one layer could be like the input of the other, and so on, until you get the result at the end. And you can see in the paper they say that they use the DCNN in their algorithm, and this is how do they get the data. So they have the data from 1,050 patients. They get approximately 76 attributes, only the 14 most relevant one to the heart disease cases they take. There are some missing values in the column for these attributes. They fill them mostly by taking the mean value of the other for the other patients, the attributes for the other patients, and for the missing columns, sometimes the missing values in the columns, I mean. They take 80% of the data for training, and the remaining 20% is for testing, and the algorithm at the end gives us the results. These are the 14 most relevant attributes that they go with, and this is the things that they calculate in the paper, which is the accuracy, precision, recall, and F1 score, with false and true negatives and positives. And this is their results at the end. These are their results at the end in the paper. They get the accuracy, interesting, they get the accuracy as high as 91%. And these are the models that we worked on. I'm gonna hand it on to Pratik to discuss it more.
So as Marshall mentioned that the paper got an accuracy of more than 91%, which was pretty high. So we thought of creating two models. V1 is basically the same model that author has used. V2 is a modified version that we came up with. So the reason why we did that was because of the data abnormality. So particularly in these three columns that you see here, which talks about thalassemia, major vessels, and a few more important segments within the heart diseases, it has those many number of NAN values, which is approximately more than 600. And now we had like 900 data points, out of which 2/3 was missing. So replacing those values with mean value or median value didn't really make a lot of sense for us. So we thought of modifying the model itself to understand the limited data that we already had. So this is the model architecture that for V1, that is the author's model. Just simple to 1D CNN, 8 dense layers. They're using ELU as activation function and Adam as optimizer. And we kept a lot of things similar, except for a few features that was changed in our model. We reduced the dense layers to only 2, and we changed the activation function to ReLU instead of ELU, and optimizer was Adam, and the loss function was mean squared error. However, we did also increase the dropout rate for 5% instead of 3%, kept the same train and test split. We kind of named this as BMK after our last name initials, and it also resembles to like RBMK, if you guys know what it is. It's the Chernobyl reactor. Hope it doesn't fail like that. Coming to the results. So this is the data that we did also experiment with the same method of replacing the values with the mean values. And we see there's a lot of choppiness in the data, a lot of fluctuations, and that's from the author's results. And now our analysis was like basically the model isn't getting enough data to learn and adapt, and that is why the accuracy isn't really matching up. We did try it with the V2 model, and we see that there's a consistency in the growth of the accuracy for validation and both the for the train. Now, same happens with the loss function. We see there's a lot of fluctuation happening. There isn't really a like monotonic decrease in the loss function as the epochs keep increasing. However, with the V2 model, we see like a smooth descent with the loss as well. Even the confusion matrix. For the confusion matrix, apparently it seemed to be having a little better accuracy than what the curves showed. However, when we try to remove those values instead of replacing those values, we see a huge misconception and confusion happening within the model to identify disease or no disease. However, the V2 model was significantly better to that. And even with the ROC curve, we see that for the author, they got an area under the curve of 91%. And when we tried with our model, we seem to have a very good amount of score of 90.29%, which we were really happy about, to be honest. And after this, I would like to hand it over to Rahul.
Yeah, so that's about like heart disease, but we also wanted to explore more about CNNs, and to do that we had to use 2D CNNs rather than 1D CNN. So the other application in healthcare using CNN is brain tumor detection or tumor detections. So we referred to the paper that I'm going to show. Yeah. So main reason why we wanted to use 2D CNN is because tableau data is not very uniform, but images are very uniform. They have a pixel range from 1 to 255. So that makes CNN work better for these. And this is the paper that we referred for brain tumor analysis. So in this, they use a simple 2D CNN model using 3,264 MRI images on brain, and they try to classify those images into 4 types of brain tumors and 1 healthy case. So 3 types of brain tumors and 1 healthy case. So yeah. So this is the model that they have shown in the paper. It's a bit complex, but I will explain in short. So it's like 64 neuron lanes, then 32, then 16, then 8. And in the end, they have a dense layer with 4 neurons, so that it can like predict which are healthy or tumor. And they use ReLU activation function. For the last step, they use softmax activation function to classify out of these 4. And yeah, so this is the results that the author get. It was actually very good. They got like 90% above. But you can see that there is a lot of like discrepancy in their data in case of model loss. And there is some fluctuations. So when we exactly replicated their model, we got some kind of decent results. We got like 80% in train accuracy and around 65 to 70% in validation accuracy. So the reason why we didn't get that much good validation accuracy is because the number of healthy brain cases is way less compared to the number of tumor cases. So then we introduced task weights. So as we give more priority to non-tumor cases, there was a bit of improvement in both validation and train accuracies. But we still see some kind of, you can say, overfitting in the model because there is a huge gap between train and validation. So to reduce that, we reduced the number of complexity of the model because we were not using that many images because it's very hard to use CPUs and train those images because it was taking a lot of time. As we reduced our complexity, we got like decent improvement in the overfitting. And yeah, and then we tried one more thing, which is just a fun activity. We tried the 1D CNN model that we discussed, that Pratik discussed, on the images. And any guesses like what happened? Will it improve? Will it like decrease? Okay, so it's actually stayed same. So when we use 1D CNN to train on the MRI images, actually we got similar results to what we were getting for 2D CNN. So that's an interesting thing we wanted to explore. And actually we got like very good results for no tumor cases, but there was some discrepancy in glioma. So the limitations that we found was like we didn't have very good GPU power, so that was one of the things that was missing. So we couldn't really train the images in every orientation. We wanted to rotate the images, flip the images. We can't really do that because it was taking a lot of time. And we wanted to try different parameter space combinations, but we couldn't do that. So future work is we'll try getting a good GPU and then try rotating the images like data augmentation. And then to reduce overfitting, we'll try like more different filter sizes, learning rates, dropout rates. And we also want to do like X-ray images analysis, like getting tumors in lungs and liver. So that's our plan. Thank you. And
Yeah, just one last, like the reason behind trying the BMK architecture on the brain tumor was basically instead of training the toddler how to walk, we were already taking a kid who knew how to walk and training him to learn. So that was the idea behind it, and it seemed to turn out fine, but we would need to kind of fine tune it later. Yeah. Thanks.
thank you.
All right, questions?
Why do you think the 1D CNN performed as well as the 2D?
Yeah.
So I think the reason is because if you see 1D CNN, we increase the first layer from like 128 neurons to 6400 neurons, so that it can train the same 80 cross 80 as 2D CNN. So it's kind of recognizing the same patterns because we increase the complexity size like by a large amount. So yeah, that's one of the things. That's a good point.
So the paper used an exponential.
Yeah. Yeah.
So why? So what was the difference first of all?
So exponential linear unit actually lets the negative value transform into like an exponential term. However, the ReLU, that just lets the value like, so if you look at the function, it goes something like, so if you have x and if it is greater than 0, then it will just let x pass by. But if it less than 0, it's just not put 0 in there. So it doesn't let the negative value go out. It just lets the positive value go in. So it kind of chops out the negative values going in the function. So that's why ReLU, if you look at the curve it has, it's just like this.
So why did you switch though?
Oh, because it is much more simpler than exponential. Exponential takes care of the negative values in a different way, and we thought maybe reducing the complexity of the model will help us because we had limited amount of data, so reducing the complexity of model will be much better to deal with it.
So a few further questions also about the 1D CNN to a 2D CNN. So in terms of the inputs, so these are images for the case that you looked at for tumor. So how did you then convert these images into let's say data format that a 1D CNN could handle? And what would it say indeed, yeah, if it does do equally well about the patterns that it can detect? So those are two questions, like how did you actually prepare the input then, and then if it works equally well, what does it mean?
Okay, so we just flattened the array, so it was like 80 cross 80 metrics, and then we just flattened it into like 6400 size array,
Yeah.
and then we just input it into our 1D CNN model, just created yeah. And for the pattern recognition, I think because the kernel size is small for the V2 case, it was able to catch some of the small tumor patterns,
Densities,
increase in pixels, relatively good compared to 2D CNN as well. So it was, I think it's because we kept the model very less complex, and the kernel size small. It was able to recognize the patterns pretty well, like 2D CNN could. Because 2D CNN is like a small 2D matrix that is going across. We kept the same size, and it was going in an array. It was able to find the pixel change very well.
Yeah, yeah, that's interesting because if it's just, and that makes sense, it's just a vector and then you have a 1D, so then you can only have, as far as I understand that, let's say filters, if you think about the weights, right, as filters, that would detect patterns that are indeed in that vector shaped format. So if it's a pattern that is really 2D and it would span multiple pixels, do you think your 1D CNN could detect that as well, or do you think that's
I
different?
think so. It can, because it's if the pattern is like a tumor and it's getting flattened, so it will be present at some certain range of window of that array, and if our model trains very well, it can recognize that kind of pattern again and again and again, and then predict as well.
Mm-hmm. Do you think that the depth of the network matters there for?
Yeah, I
being
think
able
it
to-
can matter. Yeah, we have to explore that, but it can matter. Yeah, the kernel size and the depth can. change.
So that is another thing that we were even thinking of, like by looking at like how Karnak did with the other day, number of neurons versus number of layers, thinking of like how we can actually fine tune this model into having much more better prediction with these factors coming into account.
Yeah, okay. So one more question related to this then. If you think about images, just natural images, and not just indeed brain images where you could detect tumors, then in those applications, you think about maybe self-driving cars or something, their 1D convolutional networks aren't really used, right? So why would that be, given that for your case, the networks do similarly well?
Yeah, my initial guess is at this point when you're doing something with the self-driving car kind of situation, you're actually looking at a three-dimensional space, and here the depth and the although left and right, both the x and y axis will be extremely crucial. However, when you're looking at an image of a brain tumor per se, we sort of are looking at one particular spot within the brain where we identify certain type of tumor to be present. And if you even flatten it, you know that even after creating that kind of transformation, the region would relatively be in a particular range. However, with the self-driving one, even if you transform it to like a one-dimensional thing, you're losing information here, which is significant amount of information than like having a tumor image or something. That's my initial guess at this point.
Yeah. There may be more complex patterns in natural images that do
Yeah.
require maybe to have.
Yeah, like for example, if somebody is walking by and the person is like tall or something, and if you just squeeze that image into a one dimension, it might come out as a dot, and then you would not really know how to navigate and how much distance to keep from that person when you're crossing up. So I guess that's the kind of information that you're losing when you're transforming the image or the whatever the video at that point into a one dimension.
Okay. Yeah. So I have another question, and that's maybe at the first part. So that is what you listed there was okay. The data had attributes. What
Yeah.
exactly should I saw a little bit more maybe in the graph after that, right, with the missing values, but what are those attributes that you're referring to, and why did they use a convolutional neural network and not just a fully connected network maybe to learn about those attributes?
So there were like 70 something, 76 attributes in
Yeah.
total, which is basically whatever data collection you get from a patient. But the 14 ones are these 14 are the most relevant ones to the heart diseases. I think, and we said that some of them were filled in, some of them were missing, the columns for the attributes. You can imagine them as columns, and some of the data were missing. And basically, they put the data, making like the mean of all the other existed data in these columns, and they basically just fed the data into the missing ones in the paper at least. I think they used the DCNN. I think it would give a more accurate precision and accuracy. I'm not. I think it because it works on multiple layers to filter out the images, especially when you're looking at like one spot of the image. Like for example, like this image, something like that. You're trying to focus on like one spot, the heart disease of the tumor or whatever. So I do think that DCNN would work better than.
Yeah, I could imagine that for the image. I'm just wondering about the heart disease data, because those are attributes, so they're information about the person's, maybe physical makeup, etc. But they're not an image, right? So why a DCNN in that scenario?
That was one of the things we were not very convinced about. So that's why we transferred it
Yeah.
to brain.
We tried to the brain tumor as well, the data for there to see.
Because in the paper we tried to replicate with the V1 model, but we were not able to get the same values as mentioned in the paper. So that's why this is one of the reasons we switched to brain tumor cases, because that's a good application now.
But in the paper, they did decide this was a good model for some reason, right? They did use it. So is there any?
So they had like a column within the paper where they compared different type of models like like normal CNN and like MPIs and those ones, and even I think SVMs and few regression models, and they looked at the accuracy that these models are able to predict with the same amount of data that they already had, and they for some reason they had like 91.7% accuracy with DCNN. Honestly, we were very, I want to use a good word here, unsure about the accuracy that they got. So we thought of testing it out, but our conclusion ultimately was very, otherwise. So we decided to go with the brain one, but our conviction is that for tabular data like this, it would be actually better. That's our conviction at this point. We don't really know if that's true, but we think like SVMs or some regression models would be potentially better at these things than the DCNN at this point.
Okay, yeah, even they that's not what they showed, right? And
No.
maybe there's reasons to think that in these data there are some patterns that you could think of as, that you could detect with filters,
Yeah.
where there's correlations between variables, for example, that they have as attributes. You could imagine this, right?
I think, yeah, you're right, and especially with the attributes itself, like one of the attributes which they had was location. Now, they didn't include that when they were looking at the analysis and selecting the features, but I feel like maybe that was also a good feature itself if you're looking at it, because sometimes there are certain locations where certain type of, let's say, fast food restaurants are much more popular, and it's a city life or something. So you have a different eating habits which will eventually affect the heart problems more, right? So I think for that kind of situations, maybe they wanted to try with like deep neural network and see the pattern within itself. But that's, yeah, for now I think we just feel like maybe using a normal regression or an SVM model kind of things would be potentially much more suited towards these tasks.
Okay, thank you. Let's move on. Who wants to go next? I saw initial hands. Okay, many people. I think over there in the back, maybe, yeah.